Thank you. Hello, everybody, and welcome to Code Indexing, how language servers understand our code. My name is Vinny. I'm a part of the Ruby developer experience team at Shopify. We work on different aspects of the developer experience for Ruby. For example, you might have watched Emily's or Alex's talk about gradual typing, which we are involved with. You may have also watched Stan's talk yesterday about building a debugger. We contribute to Ruby Debug. And in this talk, I want to tell you about the Ruby LSP, which is another tool that our team is working on. If you want to know a little bit more about my work, you can find me at Vinicius Stock on Twitter and GitHub. So to start off, what is a language server? As the specification describes, a language server is a background process that runs on the developer machine to provide features for any editor for a particular programming language. And it does so using static analysis, so it doesn't have access to the runtime of the language. The idea is that the editor here, the client, spawns the language server process and keeps handles for standard in and standard out in order to communicate with the language server using JSON. So for example, if a user is interacting with the editor and they request to go to definition for something, the editor is responsible for translating that action that the user took into a JSON request. So in this particular example, it would be a definition request. The language server, in turn, is responsible for fulfilling those features for the user. So it needs to find where the definition exists, return that as a JSON response to the editor, and then finally the editor will use that response to perform the action that was requested, jumping to the definition location. All interactions between the editor and language servers are exactly like this one. The user takes an action, the editor translates the action into JSON requests, and then the language server fulfills those features for the user. And because they use JSON to communicate, a language server can connect to any editor as long as the editor supports the language server protocol. And that has, in my opinion, the one very big advantage, which is that we can collaborate in improving the developer experience for everybody, regardless of which editor you use. So if someone using VS Code adds a new feature, it's not going to be only for VS Code. Everyone's going to benefit from it. Unfortunately, I'm not going to have enough time to go into the details of the fundamentals of language servers and why they were created in this talk. But if you're interested in learning more, I invite you to check out my talk from the last edition of RubyConf, where I explain some of that in more detail. The Ruby LSP is an implementation of the language server protocol for Ruby. Here on the slide, we have two different repositories. The first one is the VS Code extension for the Ruby LSP, and the second one is the language server gem. And I want to stress out the fact that the server can connect to any editor that supports the protocol. It's not only VS Code specific. And also, the server is made with 100% pure Ruby. It doesn't use other languages. So if you want to check out the repository on GitHub, you can follow along some of the examples that we're going to see in this talk. These are the features that are currently supported in the Ruby LSP. I'm not going to show every one of them, but just a few examples. We support document symbol, which allows you to fuzzy search declarations inside of the current file and also populates the outline tab on the left. We have integrations with Rubocop to display violations in the editor using diagnostics. You can also fix the violations using quick fixes, which is a code action. And you can also fix all of them at once with format on safe. And another use of code actions we have is the extract to variable refactor. So if you select any piece of code and tell the Ruby LSP to extract it to a variable, it will do it for you. And the last feature I want to bring up as an example is code lenses for tests. So we have code lenses for running tests, which are integrated with the test controller in VS Code. So it reflects the results on the panel for testing. And we also have a debug code lens, which launches the Ruby debug interactively in the editor. But to explore code indexing, we're going to be thinking about another feature that's not on the list, which is go to definition. Go to definition is not the only feature that requires indexing the code base, but it is a very good example of why we need to do it. We're going to think about this foo class here, and we're going to be considering that the user's requesting to go to the definition of the constant bar exactly at that A character in bar. When that happens, the editor sends the language server a request that looks exactly like this one. You get the URI of the text document, so the file path, foo.rb, and you get the position where the user clicked. So here, line 2, character 5, is exactly the A character in bar. What the editor expects as a response is another location, the location of the definition, the declaration location. And that includes the URI of the file, because the declaration may be in a different file, so in this case, bar.rb, and the range where the declaration exists in that file, so from line 0 to 5 in this example. Both the request and the response for go to definition are just locations. So we need to figure out what's happening in between. How do we go from the position where the user clicked to the declaration location? There are two main problems we have to solve first before we can implement go to definition. The first problem, if you think about the request we get from the editor, we only know the position where the user clicked, but we don't know if they clicked on a method call, a variable, or a constant. So the first part of the problem is figuring out what's under the cursor, what is the target of go to definition. And then after we figure out, okay, the user's trying to go to the definition of a constant named bar, then comes the second part of the problem, where is bar defined? So where's the definition of the thing you're looking for? And that's where code indexing is going to come into play. But we're going to start with part 1, which is locating targets. What we want to do is search the AST of the current file where the user clicked to discover what node exists under the position that was clicked. Basically, the language server must have the AST of the file. We must have already parsed the file, and we're going to be searching the nodes to find which one exists under the cursor. But I want to call attention to something first. Here we have our foo class on the left, and a simplified AST that we would get from parsing this foo class. What I want to call attention to is that when we're searching for the right node that exists under the requested position, it's not enough to look to evaluate if the node's location covers the requested position, because more than one node may cover it. So for example, if we take a look at the class node, it goes from line 0 to 4. So it fully covers line number 2 and the A character in bar. If we take a look at the method definition for process, it goes from line 1 to 3. It also fully covers the A character in bar. And if we take a look at the actual target, the constant bar, it also covers the location that was requested, but in a more specific way. The source, the range in the source for the bar constant is much, much smaller than it is for the class node. So more than one node are going to cover the requested position. What we're interested in is the most specific node in the AST that still covers the position that was requested by the user. The first step is converting the position we get from the editor into a string index. The reason we need to do this is because the editor sends us line and character information. But what the language server keeps in its memory is just all of our Ruby code in a string. So where in the string is line number 2 and character 5, we don't know. We need to convert into the string index, in this case, the index that will represent the A character in bar, which for our example, it's actually 28. I'm not going to get into the details of how to perform this algorithm. It's not super relevant, but the general idea is that you go through the string counting the line breaks until you find the right line, and then you add the number of characters to that. Step number 2, after we have the string index, is locating which node exists at that string index. What we want to do is go through all the nodes in our AST, searching for the right target. We're going to use 2 pointers. The target one is going to be in red, and the candidate, which is the node we're currently analyzing, is going to be in blue. And we're going to compare the proximity of those nodes to the requested index by the user to determine which one's the more specific target. If we were to visualize the algorithm for our foo class, we would start with the target being the first node in the tree, the class node, and then we would start comparing it with all of the other nodes as candidates. Here, the candidates in blue. So for example, foo, the constant foo, does not cover the A character in bar, so that cannot be the right target for Goat's definition. We move on to comparing it with the body of the class. The body of the class does cover the A character, and it is more specific than just the class node itself, so we update the target to be the body of the class. Then we move on to comparing with the method definition for process. It also covers the A character, and it is more specific than the body of the class, so we update the target again. We check the name of the method, the identifier process. It does not cover anything on line number 2, so that can't be the right target. We move on to comparing it with the body of the method, which covers the requested position and is more specific than the method definition, so we update the target again. We do the same for the method called bar.baz, which also covers and is more specific. Then we check the constant bar. It also covers, it is more specific than bar.baz, so we update the target again, and we perform one last comparison, which is checking if the identifier of the method called baz covers the A character in bar. It doesn't, so we conclude that bar is the right target for Goat's definition. In code, we can implement this as a locate method that receives the node, the initial node that we're searching inside, and the index that was requested by the user with Goat's definition. We begin by creating a queue of nodes with the child nodes of that initial node in the AST that we receive. And we initialize the target as that first node. Then until our queue is empty, until we finish going through all of the nodes in the AST, we're going to be doing some comparisons, and at the end of the loop, we return the target we discovered. If we zoom inside the loop, what we want to do for each iteration is pop the first node from our queue to be the candidate, so the blue pointer. We push the child nodes of the candidate into the queue. This is just so that we make sure to go through all the nodes in the AST and don't miss any of them. And then we start our comparisons. If the location of the candidate does not cover the requested index by the user, then it cannot possibly be the right target because it's not under the right position. If the start location of the candidate is already past the index, then we already went too far. We should have found the right target by now, and we can break out of the loop and return whatever we have stored in target. If none of those two are true, we can go on and check if the candidate is more specific than the target, because we know the candidate covers the expected position. We need to figure out if it's more specific, if it's a better target than the one we had previously. And we do that by checking the range of characters in the source code. If it is a shorter range, then we consider the candidate to be more specific, and we update the target. And we do this continuously until we figure out which one is the right target. That allows us to search for a target based on the string index in any AST we have. So we did the first part of the problem. We figured out which one's the target. And now comes the second part. How do we find out where the definition is? And that's where code indexing comes into play. In order to jump to the right definition of bar, we need to know everything that is available in the code base, because bar may not be defined in the same file where Goat's definition was requested. In fact, it may not be even defined in your project. It may be coming from a gem. So we need kind of an index object that knows about all of the classes, methods, modules that are available to your workspace in order to be able to ask the index, does this thing that I'm looking for exist? And if it does, then where is it defined? But we can't populate the index on every definition request. That would be way too slow and it would be unusable. What we want to do is initialize the index when we activate the language server, and then make sure we synchronize any file modifications so that the index is always up to date with the current information of the code base. We're going to take a look at the two parts of indexing, but we're going to start with the initial indexing at boot. And we're going to be focusing only on classes for the sake of time, implementing it in 4 steps. For the initial indexing, what we want to do is for all Ruby files available in the load path, we want to read the contents of that file, so get the Ruby code, parse it into an AST, use a visitor to extract all of the class declarations found inside of that AST, and then feed the classes to our index, which will store the information for us when we need to access it during a go-to-definition request. The first step will be implementing the visitor, so the thing that will extract the class declarations from any particular AST. And for that, we're going to be using syntax tree. Syntax tree is the gem that is the base for the Ruby LSP. If you haven't used it, it's a gem with many parsing and AST utilities for Ruby. And one of them is the visitor implementation. So if you inherit from syntax tree visitor, you get all of the visiting functionality out of the box. And all you have to do is define custom logic for the nodes that you're interested in. In our case, we're only interested in class definitions, so we can initialize this visitor with an empty list of constants where we're going to be accumulating our classes. And then every time we find a class, we just push it into our list of constants. And even though this is a very simple class, a very simple visitor implementation, it is already capable of extracting any class declarations found in an AST. So we can now extract the class declarations. We need a place to store them. We need the index implementation. The idea here would be to have a singleton object that has a knowledge hash where we're going to be storing all of those classes inside. And then the implementation for the add method receives the file path and all of the constants that we discovered in that file. And then we just do a little bit of manipulation to insert the information in the hash in the format that is more convenient for us. So in this case, each entry is going to use the constant name, and the value is going to be the file where the constant was discovered, and the location inside of that file. So if we take a look at the knowledge hash, it would be something like this. We have foo as the key, the name of the class, the path where we discovered it, foo.rb, and the location inside of that file for the declaration. Now that we have a way to extract class declarations and a way to store them, we can perform the initial indexing of the code base. The idea is to go through all files in the load path and process them with our index. Just one detail here, we're creating a URI instead of just using the file path. This will be relevant for later, even though it's not super relevant at this part. And then the implementation for process, we're going to be extracting that file path from the URI. We read the contents of the file, parse them into an AST, use our visitor to extract all of the class declarations from that AST, and then we use our add method to push everything into the knowledge object, into the knowledge hash. That's all we need to perform the initial indexing, but now we need to take care, we need to address file modification, synchronization, after the index has been initialized. Because the reason we need this is because if a file is modified, then the classes that exist in the application may have changed. If you delete a file, then everything that was defined in it is now gone. And if you modify a file, you could be deleting classes or creating classes inside of it. Thankfully, we don't have to implement file watching ourselves. Language servers can request that the editor watch files for them, and then anytime a file has been modified, it will notify the language server for us. So what we want to do is every time a Ruby file is modified, we want to take an action depending on which type of modification occurred. If the file was deleted, we want to remove any related entries from the index for that file path. If a new file was added, that file may contain new classes that we don't know about, so we have to index that new file. And if an existing file was changed, we don't know if the user's deleting classes or adding new classes, so we have to update the information in the index, remove the stale information, and index the file again to get the most up-to-date information. One way we could handle this notification would be by using a case statement. The notifications called workspace did change watched files. And then every time we receive this notification, we tell the index to synchronize the changes. And changes here, the parameter is an array of file modifications with the type of modification and the file URI. For the implementation of synchronize, we would go through each file change and take an action depending on the type of modification that occurred. So if the file was deleted, we remove the related entries for that file URI. If the file was created, we reuse our process implementation to index that file. And this is why we needed to handle URIs, because that's what we get from the editor. And if the file was changed, we want to do both. We want to remove the stale information first, and then re-index to get the most up-to-date information in the index. The only thing missing here is the implementation for remove entries for. And one way that we could implement this is by going through the knowledge hash and removing all of the constants that match the file URI that was removed. This allows us to perform both the initial indexing when we launch the language server and the synchronization if the user is modifying files. So now we're finally ready to implement go-to-definition, and we're going to do it using what we built in the other two parts. The idea is that we want to locate the target based on the position that we receive from the editor. We want to find the target in the index so that we can figure out where the declaration exists, and then return that to the editor. So we can implement the definition request by initializing it with the current document where the user clicked and the position where go-to-definition occurred. Running the request will mean using our algorithm that we saw in part 1 to locate the right target. And then in the case when the target is a constant, we know it might be one of the classes that we have indexed. So we can look for it in our index and get the file path and the location back. And then the last thing missing is returning the expected response that we saw before, a hash containing the URI of the file, where the declaration exists, and the location of that declaration inside of the file. We're done with go-to-definition. The main problems that we have to solve is locating the targets, and maintaining and managing the index is perhaps the most cumbersome part, the most complex part. But after those two parts are solved, implementing the request is pretty much straightforward. This is not yet released in the Ruby LSP, unfortunately. Most of the prototype you've seen has been conference-driven development for getting the talk done. But I do have a demo so that we know the prototype works. So this is the Ruby LSP jumping around classes in the Ruby debug project. So first we jump to the line tracer class, and then to the parent class tracer. Thank you. As I mentioned before, go-to-definition is not the only feature that requires indexing the code base. I have here a few other examples using screenshots from TypeScript to show other features that require indexing. For example, signature help shows you the signature and the documentation for a method you're currently invoking. So of course, it needs to know what the method signatures are in order to provide this functionality. Workspace symbols is kind of the same thing as document symbol, but instead of being for the current file, it's for the entire workspace. You can fuzzy search any declaration, including the ones in dependencies. So of course, it needs to know about everything that is available in the project as well. Hover, showing documentation, signatures, and even types on hover requires an index as well, so that we know which piece of documentation is associated to each method and to each class. And autocomplete, in order to provide suggestions, also needs to know about what are the available methods and constants and classes in your project. And this approach is very, very similar to what a type checker does. A type checker also has to index the entire code base in order to be able to say where a method is defined or if you're making a possible mistake. The main difference is that a type checker would probably not access the index based only on the string name of a constant or a method. It would first perform type checking and then probably use an entity representation to access the index based on an ID or something. But the code indexing part is very similar. And even in this implementation without type checking, there are still many improvements that we can make. For example, we didn't implement support for everything. We only have support for classes, so we can add the rest, like modules and methods. Building the index is very expensive. It's very slow, so we can also improve that by building it in parallel, for example, so that when we're building it from scratch, it doesn't take so long. In our explorations on the Shopify core monolith, the initial implementation took more than 5 minutes to index everything, so that's certainly has room for improvement. We can cache the index so that you don't have to build it from scratch every single time. Otherwise, every time you open the editor, you're going to pay that cost of indexing all of the files again and again. Instead, you can just have a cache and read from the cache and only index the files that have been modified since the last time you opened the editor. And we can provide options for the users to control which paths in their applications are indexed. So for example, if you have a gem that is not relevant for go-to-definition, maybe you have a linter or a formatter and you're not going to be using the classes defined in them in your project, you can exclude them from indexing, and that would speed up the initial indexing for everybody. One possible implementation of the index cache would be mirroring the project structure, say under a .ruby LSP folder, and then keeping versions of each file with the cached index. And then on start, we can read all of the cached files, and if their last modified timestamp doesn't match, then we know the information in those indexed files is stale, and those are the files we need to re-index. And this could even be a separate gem. It doesn't necessarily need to be completely implemented in the Ruby LSP. There are other gems that could potentially benefit from a Ruby index implementation. Some examples of gems that can use an index or that already use their own index is typeprof and steep. They're both type checkers, so they must index the code base in order to provide their functionality. IRB doesn't do that, but it could use it for better autocomplete results. And RDoc indexes the code base in order to associate documentation with each method or class. So all of these gems could be reusing a shared index implementation, and there are probably more than the ones I listed. I hope that you will give the Ruby LSP a try. Our team is doing a lot of effort to modernize developer tooling for Ruby, and we really believe that developer experience is an essential part in making developers happy. So I hope you join us in collaborating on improving the developer experience for everybody. Thank you.